Hi everyone. Today we're going to study classification of real numbers. Algebra uses numbers and symbols to represent words and ideas. In this video, we will describe the set of real numbers, all its subsets, and their relationship. First group of numbers is called natural numbers. This is denoted by capital N. The most basic numbers used in algebra are those we use to count objects. So we have 1, 2, 3, 4, 5, and so on. These are called natural numbers. Natural numbers are also called counting numbers. Using the set notation, we write it like this. Capital N equals the set with elements 1, 2, 3, 4, 5, and so on. Note that a radical that can be simplified into a natural number is considered to be a natural number. Example, the square root of 25 can be simplified into 5. So this is a natural number. Next group is the whole numbers. This is denoted by capital W. The whole numbers are the natural numbers and 0. In set notation, we write like this. Capital W equals the set with elements starting from 0, 1, 2, 3, 4, 5, and so on. The next group of numbers is the integers. This is denoted by Z. The set of natural numbers, their negatives, and 0 is the set of integers. We write this in set notation as capital Z is equal to ... There are some numbers on the left side. So we start here with -3, -2, -1, 0, 1, 2, 3, and so on. Using the number line, we write in the middle the 0, and on the right side are 1, 2, 3, 4, and so on. These are the positive numbers. On the left side of 0, we have this -1, -2, -3, -4. And we call this the negative numbers. There are notes here. Number 1, a negative number is a number that is less than 0. We could write a plus sign. This is the symbol before a positive number, such as +2 or +3. But it is customary to omit the plus sign and write only the number. If there is no sign, the number is assumed to be positive. Next group is the rational numbers. We denote this as capital Q. A rational number is a number that can be written in the form P over Q, where P and Q are integers and Q is not equal to 0. In set notation, we write like this. Capital Q equals P over Q such that P and Q are integers and Q is not equal to 0. Numbers under rational numbers are integers. We have some examples: -2, -1, 0, 1, 2, 3. Fractions. Examples: 4 over 5, -7 over 8, 13 over 4, -20 over 3. The decimals. But these decimals must be either stops or repeats. Examples are here. First example, 0.8. This is a decimal that stops. So this is a rational number. Another example, 2.1757575 and so on. We can see here a pattern of repetition on the 75. The 3 dots here means we can continue writing 75 on the right side of this decimal. So this is an example of a rational number. Another example, -3.25. This is a decimal that stops. So it is a rational number. Last example, -6.6. Please notice here that there is a bar on top of the 6 on the decimal. We can write this into -6.666 and so on. So the bar there means we will continue write the 6 on the right side. Now, in our second example here, this example 2.1757575 can be written like this: 2.175, and there is a bar on the numbers 7 and 5. Next group will be irrational numbers. This is denoted by capital I. An irrational number is a number that cannot be written as the ratio of two integers. Its decimal form does not stop and does not repeat. Examples: the first is pi. The actual value of this pi is 3.141592654 and so on. We can see here that it does not stop and does not repeat, meaning there is no pattern of repetition on the decimal. So the pi is an example of irrational number. Another example, 3.605551275 and so on. This decimal does not stop. Also, there is no pattern of repetition. This is an example of irrational number. We have here square root of 2 and square root of 5. These are irrational numbers. So we can conclude that square root whose radicand or the numbers inside this square root that is not a perfect square is considered to be an irrational number. The biggest group is the real numbers. This is denoted by capital R. Real numbers are numbers that are either rational or irrational. This is our illustration. The real numbers are the biggest group. Inside the real numbers are the rational numbers and the irrational numbers. A while ago, we studied some groups of numbers. Remember that the integers are inside the rational numbers. In the integers, the whole numbers are there. And in the whole numbers, we have the natural numbers. Let's do this exercise. Tick the box whenever the number belongs to the set of real numbers. The first number, -7. So this is an integer, a rational number, and a real number. Next number, 14/5. This is a fraction. It means this is a rational number and a real number. Third number is 8. This is a whole number, integer, rational number, and a real number. Next is the square root of 5. We have this example a while ago, and this is an irrational number and a real number. Next example, 5.9. This is a decimal that stops. So this is a rational number and a real number. Last example, negative square root of 64. We can simplify this into -8. So this is an integer, a rational number, and a real number. Let us have more sample problems. Problem 1. Determine which of the given numbers are rational and which are irrational. We have here 5 numbers. Let's begin with letter A, 0.36. We know that this is a decimal that terminates or stops. Immediately we conclude this is a rational number. Letter B, 0.94729 ... The 3 dots here means this decimal does not end, and we see that the digits are not repeating. So we conclude that this is an irrational number. Letter C, 2.528, but there is a bar on top of 8. We can rewrite this expression just like this. So we repeat the number 8 continuously up to infinity. Then we write this ... at the end. So this is a decimal that digits are repeating. So this is a rational number. Letter D, square root of 44. This expression is a square root of a number, which is 44. And this square root cannot be simplified into a whole number. Actually, when we get our calculator and get the value, the exact value will get 6.633249581 and so on. So this is a decimal that does not end, and digits has no pattern of repetition. That means this is an irrational number. Then letter E, square root of 49. This is a square root of a number that is 49, and we can simplify this expression into a whole number, and this is equal to 7. That means this is a rational number. Problem 2. Determine whether each number is whole, integer, rational, irrational, and real. Letter A, -8. This -8 is an integer, a rational number, and a real number. Letter B, 0. This is a whole number, an integer, a rational number, and real number. Letter C, 1.95286 ... This is a decimal that never stops, and the digits are not repeating. So this is an irrational number and real number. Letter D, 12/5. This is a fraction. Immediately we can conclude that this is a rational number and real number. Letter E, square root of 36. We check if we can simplify this into a whole number, And we can. And the value is 6. Therefore, this expression is a whole number, integer, rational, and real. Letter F, the number 9. So this is a whole number, an integer, rational, and real number.